Okay, so this next lecture is about the fasting state. And so we've already introduced just biochemistry in general. We've already talked about the fate of your fuels, what you ingest during the fed state. And now we're going to talk about what happens after your fed state. What does your body do to transition from taking in fuels to generating their own energy? So the fasting state is generally occurring 2 to 4 hours after a meal. And basically, it's triggered by the down regulation of insulin. So after your pancreas beta cells no longer sense glucose present or certain amino acids, then your insulin levels go down, and that triggers the fasting state because glucagon is always going to be present and it's ready to signal as soon as insulin goes down. So we're going to talk about different stages post-fed. We're going to talk about a 2 to 4 hour fast, overnight fast, and then more of a starvation type of fast. Okay, so we have here fasting after a meal. So this is about 2 to 4 hours. So in this case, in the blood, you have a decrease of glucose. So you're no longer sensing glucose, especially by those beta cells. Beta cells are down regulating insulin. They're no longer releasing insulin because they don't sense glucose. And you have an increase of glucagon sensing in the blood. And so now your cells are shifting from a fed to a fasting stage. And a few things occur that are critical. First off, you have those changes in the blood, and then immediately your liver kicks in releasing glucose because your liver is the main source of blood glucose. So it's going to start to break down glycogen and it's going to release glucose. Glucose will be picked up by the brain and by the red blood cells. It will not be picked up by the liver. It will not be picked up by your muscle or by adipose tissue. It's going to be spared for those two systems, the red blood cells and the brain. Now, your adipose tissue is also going to kick in and start releasing fat because fat is going to become a major source of energy for not only your muscle, but also for your liver. And so your liver and muscle will switch to using fat instead of sugar for their fuel sources. And so that's an important change. Your liver will also start to make what's known as ketone bodies. And ketone bodies are going to be a source of fat, some certain precursors making acetyl-CoA to generate ketone bodies. And ketone bodies are going to be picked up by your muscle cell. So your muscle cell will use fat, but it will prefer to use ketone bodies. Ketone bodies have a more direct mechanism of feeding into the ATP producing process. Now, your muscles are also going to start to break down proteins and release amino acids, and these are going to be used by your liver to make new glucose. So this is gluconeogenesis. And gluconeogenesis will release glucose. So you have glycogen stores releasing glucose, you have a start of gluconeogenesis, which will release glucose, and ultimately you want to maintain blood glucose level. Now, a few things to point out, which we will discuss as we go through, is that you have this green cycle here, and this is known as the Cori cycle. And the Cori cycle is basically your liver is releasing glucose to maintain blood glucose. Your red blood cell is picking up glucose because that's its only source of fuel. It can only do anaerobic glycolysis, so it's going to end on lactate. And lactate is going to be released and picked up by the liver, and it's going to be a precursor for making new glucose. So the liver can take lactate, feed it into gluconeogenesis, and make more glucose. So this is sort of a process that keeps the red blood cell fueled with glucose by having the end product, the lactate, be the precursor for the starting product, which is the glucose. Now, when the liver picks up amino acids, which can also be a backbone for gluconeogenesis, it's going to have to deal with those nitrogen, and so it's going to generate urea. And so you're going to release nitrogen. Your nitrogen levels are going to increase in your urine. Your adipose tissue also will release glycerol, and glycerol is another building block for gluconeogenesis. So that also can make gluconeogenesis. So you have your amino acids, you have your lactate, and you have your glycerol, which are all going to be backbones for making glucose during the fasting stage. All right, so 2 to 4 hours after your fasting stage, in your adipose tissue, you are going to be triggered by glucagon signaling, and this is going to cause lipolysis, the breakdown of fats. And these fats are going to be released as free fatty acids plus glycerol. And fatty acid will be fuel, and glycerol will be for gluconeogenesis in the liver. Liver is going to be starting to make, or it's going to release, I should start here. It's glucagon. Glucagon signals, and you get release, breakdown of glycogen, and release of glucose. Okay, so the first thing that happens in the liver is they're going to start cranking out glucose via their glycogen stores. They're also going to pick up glycerol for gluconeogenesis, and they're going to make glucose, and they're going to release glucose. They're going to pick up amino acids, and that's going to feed into gluconeogenesis. They're also going to make ketone bodies. Now your muscle is going to use fatty acids. So here I'm going to say no glucagon signaling. Muscle cells are not sensitive to glucagon, and that is critical. This is very, very important. And so you get no use of glycogen stores. The muscle cells do not have to maintain blood glucose level like liver, and so they want to maintain their glycogen stores for need when they exert energy and they need to tap into those quick sources. So during a normal fasting stage, when they're not undergoing exercise or stress, they are just going to simply pick up fatty acids and ketone bodies for fuel or break down protein. Okay, so ketone bodies are shown here. We have 3 ketone bodies. We have beta hydroxybutyrate, we have acetoacetate, and we have acetone. And so acetone is going to be a gas. And so acetone is basically a loss of carbons. It's exhaled as a gas. It is not toxic. Your body just simply exhales it. And it's sort of wasted carbon. However, ketone bodies are going to be generated because your liver wants to provide muscle cells initially with a source of quick energy to be used. And so ketone bodies are favored over fats in muscle cells. So we have fatty acids. So the liver will pick up fatty acids and will oxidize them to ketone bodies. And then the ketone bodies are going to be released in blood. And then these are going to be used by muscle, kidney, and other tissues for energy. So this is a partial oxidation. And then it's going to be used in muscles, kidney, other tissues, including brain. And they're going to become fully oxidized. Oops. And they're going to make energy. Okay, so now we're moving into prolonged or overnight fast. All right. And so when you start going into an overnight fast, you have to start thinking of maintaining blood glucose levels. So again, in your liver, you are going to have glycogenolysis. And gluconeogenesis. And you're going to make ketone bodies. Nothing's really changed. However, your glycogen stores will deplete. Your gluconeogenesis carbon sources are going to again be that Cori cycle. And this is your lactate. And you're also going to have amino acids, and you're going to have glycerol. And these are the carbon sources that are going to feed into gluconeogenesis. Your amino acids are usually from muscle, and your glycerol is from adipose tissue. And of course, Cori cycle is from the red blood cell. You're going to have to deal with the nitrogen, and this is going to go to urea. So now, again, here you're still at a level where you have some glycogen stores, but they're running out. And so you're going to really be depending on these three sources to maintain blood glucose levels during an overnight fast. About 24 hours after you've eaten, you pretty much depleted your glycogen stores, and gluconeogenesis is going to become the primary source of maintaining blood glucose levels. Now, for a 24-hour fast, we'll just go over this table that's in your book. Basically, you have the use of ketone bodies by your muscle cells is going to go down. So they're going to start using just fat as a source. And this is important because your brain will start to use ketone bodies. So this is going to increase. And so your muscle ketone body usage decreases and your brain ketone body increases. The brain use of glucose is going to decrease. So now the brain is shifting from using blood glucose as a source of energy to using ketone bodies as a source of energy. Liver gluconeogenesis is also going to decrease. Muscle protein degradation is going to decrease, so you don't have those amino acid precursors. You're relying mostly on the Cori cycle, lactic acid, and glycerol from your adipose tissue. Importantly, liver production of urea decreases, and this is directly related to the decrease of the muscle protein degradation. So you're no longer getting all those amino acids, you're no longer getting that excess nitrogen, and so you don't have that increase of urea production. Now, when you start to go into starvation, which is a fasting of more than 3 days, a few things are going to change, but not too much. So basically, your muscle use fatty acids for fuel, and they are going to decrease ketone use, as we talked about. This causes, this causes increase of ketone in the blood. Okay, so the increase of ketone in the blood leads to a decrease of glucose use by the brain and increase of ketone use by the brain. And they're really sparing or saving glucose for your red blood cells. So RBC continue to use glucose and make lactate. Now your liver is going to decrease gluconeogenesis. It has no amino acid precursors because your muscle is no longer breaking down proteins. So you have a decrease of protein degradation. And this is going to be protein sparing. So it's really a lot of your metabolism at this point is going to rely on fatty acids. Of course, except for your brain and your red blood cells. Brain will use ketone bodies. It can use some fatty acids. And your red blood cells are limited because they can only use glucose. So after a prolonged fast, all these dotted lines now are going to be decreased. And you're really going to push your ketone bodies to your brain, and you're still going to have this Cori cycle going, but the amount of glucose being produced is going to be decreased because the amount of proteins being degraded, proteins are spared, and so they're not going to be degraded. And so you don't have this feed-in source, and you don't have this push to urea. You still have your glycerol because your fatty acids are still being released and used as a major source. So you're basically at a prolonged fast, a 3+ day, you're conserving muscle protein. And you're going to be using fatty acids more for all your cells. And the liver is going to depend on glycerol and lactate for making glucose. So keep in mind that blood glucose must be maintained. And it's going to be at about 80 to 100 mg per deciliter. So basically, if you can't maintain this blood glucose level, then you're going to be pushed into hypoglycemic. If you're a diabetic, you have too much glucose, you're hyperglycemic. So after about 3 to 5 day fast, your muscle are going to decrease ketone use. And they're going to increase fatty acid use. And so fatty acids is going to be a major fuel for tissues like muscle. Liver will make ketones, bodies, and brain will use ketone bodies. And the glucose will still be required by your red blood cell because they cannot use anything else. Now keep in mind about So here's a side note. Approximately 24 to 30 hours after your fed state, your liver glycogen stores are depleted. And so adipose tissue release fatty acids equals a major fuel for liver, muscle, etc., except for your brain and your red blood cell, basically every other cell. Okay, so muscle decreases use of ketone bodies in a prolonged fast. And so this is a trigger for the brain to switch over to ketone bodies because the levels of ketone bodies are going to increase. And the levels of glucose at this time decrease. So that's another trigger for the brain not to use glucose, to save the glucose for the red blood cells. So the liver is going to use fatty acids not only for fuel, but also to make ketone bodies. And it will use glycerol plus lactate to make glucose. Muscle, again, will use fatty acids, not ketone bodies. Red blood cells always use glucose. Okay, so as a recap, we have 1 hour after meal. We have glucagon signaling in liver, and this triggers release of glycogen stores and start gluconeogenesis. And in the adipose, you have release of fatty acids plus glycerol. In muscle, no effect. They are not sensitive to glucagon signaling. In red blood cells, no effect. Not sensitive to glucagon signaling. And then by 2 hours after a meal, you're going to again go into a fed state. If you eat again, you go back to fed state. If you fast for 12 hours, this is going to be a basal state. So it's post-absorptive. And in this case, serum insulin is very, very low. All right, so this is different tissues, just to go through the metabolic activities of different tissues. Again, the liver is going to be important for making or maintaining blood glucose levels. So the liver has ability to do gluconeogenesis. You have, of course, no ketone body use in the liver. They make ketone bodies. They do not use them for fuels. They are going to use fatty acids for fuels. And then, of course, they are going to also be the one that forms urea. And then when you go to adipose tissue, you also have adipose tissue does not metabolize fats, which makes sense. They release fats, they don't use them. They can use some ketone bodies, but not much of the ketone bodies. And then your kidneys So there's a difference between the cortex of the kidneys and the medulla of the kidneys. The cortex of the kidneys, just to point out here, has the ability to do gluconeogenesis because the medullary area of the kidney is poorly vascularized. And so a lot of those medullary cells rely on glycolysis or anaerobic glycolysis for their fuel. So they have to have keep and maintain glucose levels within the kidney. And the kidney cortex cannot compensate for liver failure for maintaining blood glucose level for a long time. Just keep that in mind. Muscle, of course, is going to be important for using ketone bodies. It's also going to be able to use fats, etc. Keep in mind, muscle cells are not sensitive to glucagon. Brain, on the other hand, is not really going to oxidize fats too much. It does like to use ketone bodies, and it does like to use glucose, of course. And then red blood cells only have the ability to use glucose, so they produce a lot of lactate. Now, just a quick note about urea and what's going on with our nitrogen. So you can see this gives you an amount of nitrogen excreted, and the most is going to be after fasting. And this makes sense because this is when you're still tapping into your proteins in order to make glucose. Starvation up to 3 days, you still have your proteins being tapped into. When you start going into major starvation, this is where you have protein sparing. And so overall urea concentrations, that's what this is, decrease with increase in starvation because you're trying to spare your muscle protein. So muscle protein breakdown is going to be spared. Tissues are going to switch to using ketone bodies and fatty acids instead of glucose to spare glucose for your red blood cells. Death by starvation is when loss of approximately 40% of your body weight. So this is going to be about 30% protein loss and about 70% of your fat stores. Starvation occurs at about a body mass index of 13 for men and 11 for women. Normal ranges are about 18.5 to 24.9, for example. Okay, and so this is the end of our fasting lecture. So again, we're talking about we have blood glucose levels dropping, insulin goes down, glucagon takes over, glucagon signals. Primarily, it's going to affect your liver, your adipose tissue. It's not going to have any impact on your muscle, which is very important. You're going to have a shift of fuels depending on how much time post-fed you are. If you're in a normal daily cycle, the longest fasting is usually about 12 hours. So you still have glucagon stores in your liver. If you go to about a 24-hour to 30 fast, then your glucagon levels in your liver decline and you're maintaining blood glucose levels simply by gluconeogenesis. As you go towards a more prolonged fasting, your liver is going to switch from using ketone bodies to using only fatty acids. Your brain is going to switch from using glucose to ketone bodies. Your glucose is going to be spared for your red blood cells. As you go further into fasting, now your proteins are starting to be spared so you don't break down muscle so much. And fatty acids and release of fatty acids is going to be primarily energy source for most of your organs except for the brain, which uses ketone bodies, and your red blood cells, which continue to use glucose. Okay.